All right, so now we're going to go over what some of you missed in class when we initially talked about angular momentum. So we're going to start with a question. So we had a demo in class where we had two disks set up on one of our vernier setups, and we set disk A spinning at about 10 radians per second, and we dropped an identical disk called disk B on top of it that had these little cork feet, so they stuck together when they fell, and we wanted to predict what was going to happen to the angular velocity of disk A when this happened. We then also did an experiment where we dropped a disk that was heavier, that was twice as heavy as disk A, and see if that would change it. And then we also did a little thought process of what would if disk B was made out of ice? How would that have changed our answer? Now, this situation might sound familiar to something we did in class before. So this is very similar to a case where we had two carts colliding, where we had one cart that was at rest and another cart was crashed into it, and they had Velcro things that made them stick together, and they moved along afterwards. So in that case, we observed that the carts moved slower afterwards. And the idea of physics we used to predict that situation was something called conservation of momentum. So we're going to use another concept that's similar. We have previously used conservation of linear momentum, so now we're going to use conservation of something called angular momentum or rotational momentum that's going to follow some of the similar rules. And we can also realize that our rules of conservation also apply to this. So we can have this idea of something called angular momentum. It's a vector quantity that's in the direction of the angular velocity. And the angular momentum follows the same conservation laws as linear momentum. Now, they're not going to be in the same equation, but we have this idea that linear momentum of all objects during interactions is conserved unless there's an outside force, and angular momentum of all objects in an interaction is conserved unless there's an outside torque applied to it. So our equation for linear momentum from previous chapters was momentum equals m times v. And we're going to have a similar equation for angular momentum, which is the angular momentum, we use the capital L for that, equals the moment of inertia times the angular velocity. Now, if we look at our units, linear momentum had units of kilogram meters per second. Angular momentum is going to have units of, let's see, moment of inertia has units of mass per distance squared, so kilogram meters squared, and then its angular velocity has units of per second or radians per second, so we get units of kilogram meters squared per second. So let's go back and analyze the situation and see if we can use our theory now to predict what we saw with our experiment. So again, we're going to start with our simple conservation equation. Start with our simple conservation equation, which just says that before the interaction, or in this case we have two objects, so we're going to say the angular momentum of object A initially plus the angular momentum of object B initially, I'm going to use 1 for before and 2 for after, equals the angular momentum of object A after the interaction plus the angular momentum of object B after the interaction. So you always start by writing out our conservation equation. Now let's look and see if anything is 0 to make our life easier. In this case, object B is not spinning before the interaction. There is no angular momentum of it, so we can drop out that term. It's going to go to 0. And now we're going to expand our terms. And remember, we said that angular momentum is equal to the moment of inertia times the angular velocity. So we have the moment of inertia of A times the angular velocity, which we call omega 0. And that's going to equal the moment of inertia of A times the angular velocity after the interaction plus the moment of inertia of B times the angular velocity after the interaction. And since they're both moving together, they stick together, we only need one final angular velocity in this situation. Now, a couple other nice things happen here. Since it says they're identical, we can say that the angular velocity of A is equal to the angular velocity of B. So that means that all of our angular velocities are going to, in this case, are going to drop out. And we get that our final angular, or initial angular velocity is going to be equal to omega 2 plus omega 2, which is 2 omega 2, which means omega 2 is going to equal 1/2 of our initial angular velocity, which is what we saw in class, that the angular velocity went from 10 radians per second down to 5 radians per second. All right, so there's case A. So our theory, conservation of angular momentum, does back up what we saw in class. Now, what if disk B were 200 grams? Now, if disk B were 200 grams, I'm just going to erase these to go back in time a little bit. my moments of inertia are not going to cancel out this time. But I can say, this is not going to be true anymore, but I can say that the moment of inertia of object B is equal to twice the moment of inertia of object A. Since in this case, moment of inertia for a disk is 1/2 mr squared. They're the same size, they have the same radius. The shape factor is going to be the same. It's just that B has twice the mass, so it should have twice the moment of inertia. And if I sub this in now, so wherever I see, I can say moment of inertia A times omega naught equals moment of inertia A times omega 2 plus, now moment of inertia B, I'm going to turn into 2 moment of inertia A's times omega 2. Now these moment inertias will drop out again, but I get omega naught is going to equal, let's see, omega 2 plus 2 omega 2. So omega 2 is going to equal 1/3 of my initial angular velocity, which again is what we saw in class. When we put the heavier disk on top of the same size, just more mass, it slowed down more. So in this case, this is very similar to linear momentum, except for it includes this rotational momentum or angular momentum. And in our case here, when these things interact, the total angular momentum has to stay the same. But in our case, object A lost angular momentum and object B gained angular momentum. But the total for the system had to stay the same. Now for the third part up here, it says, would your answer change if the second disk was made of ice? What that is really assuming is usually when we say things are made of ice, it means there's very, very little friction. Now if we think about why is the angular momentum changing here, it's because remember, regular momentum changes because there's an outside force acting on our object. Angular momentum changes because there's an outside torque acting on our object. Now if this are made, where's the torque come from in this case? It comes from friction between the two disks. If the disk B was made of ice and there was no friction between A and B, B couldn't apply a torque on A, it couldn't change the angular momentum of A, and A would just keep spinning the same way as it was, or I guess in real life it would just, its angular momentum would change very, very slowly because the torque on it would be very small because the friction force would be very small. All right, let's try one more. So this case, it's similar, but instead of dropping a disk onto our other disk, we're dropping a sandbag. So it says disk is set spinning again. You drop a sandbag on it. You can either drop it on the edge or you can drop it in the center. What will happen to the angular velocity of the disk after each case? So in this case, we are, and I'm going to say, B says like in the center. Let's just say it's a little bit off the center just to make our life a little bit easier, to make it a little more realistic. But again, we can use our idea of conservation of angular momentum to solve this case as well. So we're going to say in the beginning, the sandbag is just not moving at all. So there is no angular momentum or linear momentum of it. So in this case, we can say that the angular momentum of the disk in case 1, or in time 1, that's all that there is. And that's got to equal the angular momentum of the disk at time 2 plus the angular momentum, since the sandbag drops and we're going to assume it stays with it and spins along with the disk, of the bag at time 2. Now again, we have to expand these. So we're going to have the moment of inertia of the disk times the initial angular velocity equals the moment of inertia of the disk times the final angular velocity plus now the moment of inertia of the sandbag. And since we're going to assume it's moving with the disk times the same final angular velocity. So in this case, they are not just identical shapes, but what's the difference between A and B? Well, let's take a look. So the moment of inertia of the disk is going to be, again, 1/2 m radius of the disk squared. And the moment of inertia of the bag, now let's assume the bag is small in size compared to the disk, just to make life easy right now. So that's going to we can treat it as a point mass. That's going to be actually this should be the mass of this, the mass of the bag times the radius, I'll put radius B, the radius the bag is dropped at. So how far from the center point, the pivot point of the disk, the radius or the bag is dropped onto. Now this is not going to be as clean as the last one because things aren't going to drop out as easier, but we're going to see it's not too bad. Let's first solve this for our final angular velocity. Let's see, we can pull out an omega 2 over here. And then we can solve it for omega 2. So we get omega 2 is going to be equal the moment of inertia of the disk divided by the moment of inertia of the disk plus the moment of inertia of the bag. That whole thing divided by the initial angular velocity. And now we can actually look at this and see the answer to our question. Since for both cases, the top of this is the same, this is the same. The only thing that's different is the moment of inertia of the bag when we drop it in case A versus case B. But since the moment of inertia of the bag, since we're assuming it's a point object right now, is the mass of the bag times the radius that it's dropped at, well, in case A, the radius is much, much bigger. It's farther away from that center point than it is in case B. So the bottom of this fraction is going to be much bigger. That means the angular velocity is going to be smaller in case A than case B. So it's going to end up rotating at a slower rate in case A than it is in case B. And again, a way to think about this is the disk spinning has some angular momentum in the beginning. It has to lose angular momentum to give it to the sandbag so that the sandbag has angular momentum at the end. And since they're spinning the same at the end, the sandbag is going to need more angular momentum when it reaches the same angular, or when the two angular velocities kind of converge on each other in case A than it would need in case B. So more angular momentum is going to be lost by the disk. More is going to be gained by the sandbag in the case A versus the case B case. So we can say that in the end, that the angular velocity in case A is going to be less than the final angular velocity in case B. And again, if you wanted to solve for these things, you could plug your numbers in. I believe in case A, you get something like something around 11 radians per second that you can do for practice. And I think in case B, you almost get no change at all because the radius is so small. You get something around like 19.8 or something like that radians per second. But again, angular momentum is conserved. The disk loses some, the sandbag gains some. In this case, the bigger the moment of inertia of the sandbag afterwards, the more momentum it's going to have, the less the disk is going to have. All right, let's try one more. It's a little bit different this time. So here we have a dog, Rocco, is riding in the center of a roundabout, and he decides to carefully trot out to the edge, always walking directly away from the center, and we want to know what's going to happen to the speed of the roundabout as he reaches the edge. So again, we're going to model this as a disk, and we're going to model Rocco now. Because Rocco is moving, we're going to have to be a little bit different here. Rocco, we can't really assume that Rocco is tiny compared to, or has no size compared to the disk in this case. So we're going to model Rocco as let's model Rocco as, I guess, a sphere, we can say that. So we can say the moment of inertia of Rocco is going to be 2/5 mass of Rocco times the radius of Rocco squared. And we can say that the moment of inertia of the disk is going to be 1/2 mass of the disk times radius of the disk, I'll call that big R, squared. I guess I called it RR, whatever. So it's the 2 meter thing. And let's set up our conservation equation and see if we have to do anything else with our moments of inertia. So again, in the beginning, we have the angular momentum of the disk, or the roundabout, plus, I'll call it disk because otherwise there'd be too many R's. The moment of inertia of Rocco, and that's going to equal, that 0.1 is going to equal the the angular momentum of the disk at time 2 plus the angular momentum of Rocco at time 2. Now again, we can expand these. So Rocco is rotating in the beginning, so none of these are 0 this time. We're not dropping Rocco on it. He's on the roundabout spinning around with it and just walks towards the edge. So we have moment of inertia of the disk times omega 1 plus moment of inertia of Rocco times omega 1. And that's going to equal the moment of inertia of the disk times omega 2. Now, we got to be a little bit careful here. Plus moment of inertia of Rocco times omega 2. Now, it seems like everything's just the same, but let's think about what's happening here. As the disk spins, the disk is staying a disk, but what's changing? Well, where Rocco is on this disk is changing. So in the beginning, Rocco is rotating right at the center of the disk. So the kind of center rotation is through the center of Rocco. But when Rocco starts walking away, his effective moment of inertia with respect to the disk is actually changing. So I cannot assume Rocco's moment of inertia is the same. So we're going to have to say he has a new moment of inertia. So what is that new moment of inertia? Well, this is a nice case where we can use the parallel axis theorem. So we can say the moment of inertia of Rocco as he walks out is going to be his moment of inertia, because in the beginning it was his moment of inertia through his center point, plus his mass times how far he moved, which is he goes from the center right to the very edge. So that is just what we call capital R squared. So that is Rocco's new moment of inertia. So we can already kind of see, if we want to solve this for, again, what's going to happen to this angular velocity. Well, we can kind of combine some terms a little bit. We can combine the moment of inertias on the left side divided by omega 1, and we can combine the moment of inertias on the right side and pull out an omega 2. And again, if we solve for omega 2, we get that is equal to the sum of the moment of inertias before Rocco walks divided by the sum of the moment of inertias after Rocco walks out times the initial angular velocity. So now we can see that since Rocco's moment of inertia is getting bigger, the bottom of this fraction is getting bigger, and therefore the final angular velocity is going to be less than it was in the beginning. And again, I'll leave it to you to finish up doing the math of this. You can plug in your numbers and figure this out, and you get that it drops to, I think, something around 7 radians per second, I believe, if you solve this out. But again, what's different here is, it's a little bit weird, we're changing the angular momentum not by spinning something faster or slower, but we're changing the angular momentum by changing the moment of inertia of one of our objects. All right, let's go through one more. Now this one's a little bit different. So here we have an object, or kind of like a bar, and a ball is shot at it. And the ball sticks to the bar, and then the bar starts to spin around. And we want to kind of figure out what's going to happen here as this happens. So again, this is a question of an old test. So the first thing says it wants to know what's determine the moment of inertia of the rod and the moment of inertia of the disc. I guess it's here, it's a disc is hitting it, kind of could be a ball, whatever you want to call it. Immediately after they collide. So again, we're going to assume that the disc is very small compared to the bar. So we can assume that it's basically like a point mass again. So the moment of inertia of the bar would just be, now it's a bar rotating around its edge. So we could do some calculus to find it, or if you remember from doing this before, ends up being equal to 1/3 ml squared. In this case, L, they use the variable d, so it's going to be 1/2 m, or 1/3 md squared. That is the moment of inertia of the bar, and they call the mass b, so we might as well use, or actually I called it rod. So let's be careful, make sure we use the correct variables given the problem. And the moment of inertia of our disk, since we're assuming it's a point mass because it's very small compared to the length d, we can say that is equal to just the mass of the disk, which I called times now. After they interact, since it's spinning around this pivot point, it's a distance x from the pivot point, so this should just be the mass of the disk times x squared. Right, part A, not too bad, just a little review. Part B, oops. It says derive an expression for the post-collision angular speed of the rod. Express your answer in terms of d, m, x, v naught, and physical constants. And it tells us the mass of the rod is 3m and the mass of the disk is m. So basically the rod has 3 times the mass of the disk. Now again, we're going to start by using conservation of angular momentum. So we can say the angular momentum, or the total angular momentum initially, equals the total angular momentum after they interact. So what makes up these things? Now, it seems like there's no angular momentum in the beginning because there's nothing spinning. The rod is stationary and the disk is moving in a straight line. Now, this is when it gets a little bit kind of weird for our brains a little bit sometimes. So in this case, even though the disk is kind of moving in a straight line, with respect to the pivot point, it does have an angular momentum. And we can find this angular momentum. We can say the angular momentum is equal to or r cross p, where r is the distance from the pivot point to our object. So, and when something has a linear momentum, but it's not moving in a line that goes through the pivot point you care about, it effectively has an angular momentum in this system. And its angular momentum is defined as r cross p or r cross mv, and that ends up being a type of angular momentum in this case. So, and now in our version, in the beginning, we do have, so the disk has some angular momentum. So we have angular momentum of our disk at time 1, and that's going to equal the angular momentum of the rod at time 2 plus the angular momentum of the disk at time 2. So that's the tricky part, is that the disk actually does have an angular momentum. We can say the angular momentum of the disk equals r cross p, which equals the distance that it's at, so r mv. And now in our case, r is just this distance x times the mass of the disk is just m, and then v is what we call v naught. So the disk does have an initial angular momentum. So we can expand these. This is just x m v naught equals the angular momentum of the rod. So that's going to be its moment of inertia times the angular velocity after they interact. Plus, now we can treat, once they stick together, we can treat the disk as a point mass. So its angular momentum ends up being, so let's say the angular momentum of the disk times omega 2 as well. Now if we expand these a little bit farther, we got x mv naught equals the moment of inertia of the rod. Let's see, we said that was 1/3. And the mass of the rod was 3m. And the length of the rod was d squared times omega 2 plus, now since the disk green tree is a point mass, this is just going to be m, let's see, x squared times omega 2. And we can kind of group things. Now be careful, we can cancel the masses out even though they had different masses, and we did kind of convert them this way. So each term has an m in it. So that is going to go away. And we end up with, let's see, we can divide. It's going to be a little bit of a mess. But let's see, we're going to try to solve for omega. So let's pull the omega 2 out. So we got, let's see, the 3 cancels the 3. We get d squared plus x squared. We pull an omega 2 out. And then if we divide both sides by that, we get that omega 2 is going to be equal to x v0 over d squared plus x squared. And there is our final angular velocity after the disk hits this thing. So again, another situation where angular momentum is conserved. It's just in a little bit different, weird way. Here we have this object where it has a, it seems like it doesn't have an angular momentum because it's moving in a straight line, but in our system, since our system is defined, we're defining it by the pivot point over here, the disk moving does have an angular momentum, at least in our system, and its angular momentum is defined by that. So there's a couple problems involving conservation of angular momentum. Again, mathematically, they're not too bad. They do get a little bit confusing in our brain, and we'll talk about them more in class.